Right. So hello, everyone. So first of all, I would like to thank the organizers for giving me the opportunity to present this talk here at the Parity from Home conference. I'm very happy and delighted to be there. So my name is Léo Vacher. I'm a postdoc student at CISA in Italy, where I study the impact of the signal of our galaxy on the study of the cosmic microwave background radiation. And I would like to tell you about today the spectral distortions of galactic foregrounds and discuss with you whether or not they could be a problem for the detection and the study of cosmic birefringence. So, as most of you know for sure, there are two main sources of polarized foreground to the CMB, which are thermal dust and the synchrotron radiation. And so, as I said, both are strongly polarized. And moreover, they can produce some significant EB signals. So in the case of dust, this is through the process known as magnetic misalignment, which happens basically when the magnetic field in a filament is not aligned with the structure of the filament itself. And so there's a lot of literature on this topic that you can find easily online. And I know that Carlos Hervias-Caimapo will give us a talk at this conference, and he will present some dust models, which include this magnetic misalignment. And I'm sure he will explain this much better than I could. But so the foregrounds can produce some parity violating signals, and these parity violating signals of the foregrounds have to be accounted for at some level in the analysis when you're looking for cosmic birefringence, because if you don't, you might end up with some biases. And so this has been studied in great details by Patricia Diego Palazuelos, which is one of the organizers of this conference. And you can also find a lot of material from her online if you want to know more about how to do so. And so today I would like to tell you about some additional complexity beside the simple fact that foregrounds produce some EB. And so this complexity has to do with how the signal, and especially the EB signal, is changing with frequency. So it's spectral energy distribution. So I will tell you that much like CMB lensing, the CMB foregrounds transform B modes into E modes. They actually rotate B modes into E modes. And also the signal of the foregrounds are distorted, which means that the EE signal does not behave in frequency as the BB signal, and which doesn't behave itself as the EB signal. So the three polarized spectra of the foregrounds have different frequency behavior. And so all those effects are complex. They have to be tackled when you want to have an accurate model of dust, that's for sure. And those effects have been seen first in Planck data in a paper by Alessia Ritacco in 2023. And so Alessia will also give a talk at this conference. And so you can also ask her more questions about her analysis. And we also saw those effects in simulations, which convinced us that they were real and that we could explain them in a later paper. And so supposedly those effects could have some impact and some consequences when you do some birefringence analysis. So now at which level, I don't know. I guess no one knows, even though I had the chance to discuss this with some of you already in very interesting discussions. And so if actual data, like Planck data, are not sensitive to those effects, we might be in the future with more and more sensitive experiments. So it's good to be aware that they exist. So all those effects come from something that is called polarized mixing, which is rooted in the fact that the physical conditions in our galaxy is changing depending where you are in the galaxy. So the temperature, the dust grain composition, and also the magnetic field's orientation changes at different points of the galaxy. So whenever you're doing an observation of the sky, you're always accessing an average over different physical conditions. This is first the case, so along the line of sight here in the 3D galaxy, but also in between the line of sight. So when you have a beam, an instrumental beam, or also a pixel, a map pixel, within the pixel or within the beam, you're averaging different physical conditions over different physical conditions. And so also on the largest scales, whenever you're doing spherical harmonic transform, for example. So on the lowest multiple, you're really taking huge chunks of the sky and you are averaging over them. So why is this a problem, the polarized mixing? So first, we have to understand what we are actually averaging over. And so we are averaging over linear polarization for what is our concern in CMB studies. And linear polarization can be modeled by a complex number, which is written Q plus IU, where Q and U are the two Stokes parameters. And you can rewrite this in polar form as every complex number as P nu times exponential 2I psi. So this big P nu here is called the polarized intensity. It's the modulus of this number. And under reasonable assumption, it behaves as the intensity. And so this P nu, which is the polarized intensity, is non-linear in terms of frequency. It's a non-linear function of frequency, and this will have strong consequences. And this psi is called the polarization angle, and it's related for the ISM to the galactic magnetic field orientation locally. And it's supposedly a constant. So this is a modeling of the signal in each voxel, so in each infinitesimal 3D pixel of the galaxy. And so this P nu, the polarized intensity, is a function in general of some parameters, which we call the spectral parameters. And in the case of dust, which I will take as an example in the remainder of this talk, in the case of dust, this function is what we call the modified black body, which depend on two spectral parameters, beta and the temperature T. And so I will focus on dust, but everything I will say still applies to synchrotron or any foregrounds you can think about. All right, so whenever you have some mixing, so wherever you're averaging over different physical condition, your total signal here will actually be the sum of different complex numbers with different spectral parameters, B1, B2 up to Bn, and different polarization angle, psi1, psi2 up to psi-n, because you can also average over different magnetic fields orientation. This has several consequences. So one of them is, since this P nu function is not linear, the sum of all those P nu does not get a function that behaves as the local one. What I mean by this is that the sum of 2 or 3 or n modified black bodies is not a modified black body anymore. So the modulus of this total complex number will not behave as the individual ones here in the sum. This effect is known as SED distortions, and it's actually the same process that is going on for spectral distortions of the CMB, for example. But here you have some averaging going on in the width of the last scattering surface, because temperature can change in the width of the last scattering surface, while here SED distortions are really properties of the foreground themselves. And another consequence is that the total polarization angle of this complex number will rotate with the frequency, will change with frequency. So this total complex number will rotate in the complex plane as frequency change. So all those effects are complex, and they have to be modeled and understood if you want to perform component separation, or if you want to just accurately understand the dust signal or the foreground signal. And a good way to model these effects, even though I will not detail it because that's not the focus of this talk, is given by the so-called moment expansion, which is a method we investigated which really grasp those effects. And so if you want to know more about this, please have a look at the following papers. All right, so now we can wonder what will be the consequences of those effects, but at the E and the B modes level, which are of interest for us when we do cosmology. So let's start with a thought experiment. Consider an infinite filament in front of a zero background. And in this filament, the polarization angle in every point is aligned with the filament direction. So this is sort of a textbook study example of a pure E-mode case. So why it's a pure E-mode case? So you can show in this situation that the E-modes will be proportional to Q in this frame, the green frame, and B will be proportional to U in the red frame here. And so please have a look at this paper of Zaldarega if you want to know exactly the details of the calculation, but you end up in a situation where you have pure E. Now, imagine that there is some polarized mixing occurring. So for example, in the width of the filaments, you can imagine that the temperature, for example, is changing because there's turbulence in the filament, or you can even imagine that there's actually a background with a different magnetic field orientation and different spectral parameters, which will not change the conclusions at all for that matter. So if there's some polarized mixing, the filament that you observe like this at a frequency mu1, you will observe it like this at a frequency mu2, because a consequence of polarized mixing is the rotation of the angles. And you will not be anymore in a pure E situation at this second frequency. You will have both E and B. And so this has strong consequences. And the consequences that the consequence are that the E to B ratio first, will not be a constant quantity with respect to frequency, because at different frequency, you don't find the same proportions of E modes and B modes. And the only way for it to be possible is that E and B should be different functions of frequencies, because if they were the same, it will be a constant number. And when you translate that at the angular power spectral level, you will find that EE, BB, and EB will, the three of them will be different functions of frequency, basically. And these functions of frequency will not be modified blackbody squared because of the distortions I was telling you about before. And the EE over BB quantity will be a frequency-dependent quantity. So those are consequences of polarized mixing. So all those behaviors can be naturally modeled and predicted using moment expansion. That's what I'm just telling you that, and you can have a look more deeply in the papers if you're curious about this. And actually, we predicted those behaviors by studying the moment expansion. So it went a bit the other way around. We understood that dust could do those things by looking at the math first. And so we verified that those effects exist in filamentary dust models and also in the PySM models used by the community. And I will tell you more about those two cases right after. And we have some observational hints within the Planck data that those effects exist. And that's actually what drive all those studies, actually, to understand what we were seeing at first in the Planck data with the paper of Alessia. All right, so to summarize quickly what I already said, just like Q can go into U because of polarized mixing, E can also go into B. Because of the distortions, EE, BB, and EB will be different functions of frequency, and the E to B ratio will thus not be a constant number. It will change with frequency. And this is powerful because what you can do is that you observe this quantity, E over B, at different frequency, at a frequency 1 and a frequency 2. If you don't get the same number, you know that some polarized mixing must be there, if you're sure it's not systematics or something else. So this quantity provides a model-independent probe of polarized mixing and of foreground complexity, that is. Because you don't need to assume anything about the dust. You don't need to say it's a modified black body or a polar law or anything. Just look at E over B and you see if it changes or not. All right, and so those effects, it's critical to model them for B-mode component separation or E-mode component separation when you want to clean the CMB and access those power spectra. And so we can be sure that this will have some impact at some level also when you want to recover EB, and so when you want to study cosmic birefringence. All right, so if we look quickly at the toy model filaments, this is exactly the same case as the toy model I was telling you before, or more or less. You have a background here with in orange polarized angle and a given spectral parameter. And in the filament, you have another spectral parameter value and another polarization angle value. And what happened here is that in the filament, your signal will be the sum background plus filament. And so the total polarization angle will change with frequency as expected. And it will turn from orange to blue at two different frequencies in the filaments. If now you compute the E modes and the B modes of this 2D map, and you look at well, first, what you can see here is that the E to B ratio is indeed frequency-dependent quantity. And actually, here in this toy model example, it changed by a factor of 2, which is huge at low frequency. And also, so if you look at the E modes, B modes, and EB spectra, and you divide them by a modified blackbody squared of reference, you see that the three different spectra are not modified blackbody squares. They slightly differ from modified blackbody squared, which is exactly the consequence I told you about, which are the SED distortions. And interestingly, the three of them have different deviations from modified blackbody squared. So they do not show the same difference with respect to a modified blackbody squared. All right, so we can also look at the PySM models, which are used by the CMB community. So we consider here by order of complexity, of increasing complexity, first D0, which is given by a single modified blackbody with a constant beta and a constant temperature over the sky. So this is the simplest model, and there cannot be any mixing occurring here. Then you have D1, in which you have a modified blackbody in each pixel, but beta and T changes over the sky. So mixing can occur. Then you have D10, which is a refined version of D1, and D12, in which in each pixel you have the sum of up to 6 different MBBs with different betas and T over the whole sky. So this one is supposed to be the most complex one, and this is what we will see in the next slides. So I've been using the Planck galactic mask with 80% of the sky. So we have a large sky fraction. And I average all the multiples between 2 and 200s to focus on the largest scale. So the effect should be strong, very strong. And so you will see different effects depending on which sky fraction you consider and which multiples being you're considering. So those consequences will really depend on the analysis, the exact analysis you're doing. Okay, so if first we look at the EE over BB ratio, we see that indeed, so in the case of D0, we have no variation because you don't have any mixing. So this is a null test, but this is expected. And then you see a variation of this ratio, which is the stronger for more complex models, so D10 and D12. And so in black line here is the modeling of the moments, and you see that it's also a good model. So indeed, this ratio changes with frequency as we expected, and it's a model-independent probe of the foreground complexity because it really tells us which model is the most complex, and we don't have to make any assumption on actually what is inside this model. Now, if we look at EB, so first a little disclaimer, the PySM models don't have any EB signal in them. So, well, not physically implemented EB signal in them. So they're not the best models to study those effects, but they still give us some indications of the complexity we have to expect. But for more realistic models, then I invite you to watch the talk of Carlos exactly about this topic. So what we can do is that we take the EB signal of those models and we fit on them a beta and a t. And then we look at the deviation of DLEB with the best fit modified blackbody squared. And here you see that the more complex the model is, basically, the more deviations you have from this modified blackbody. While for D0, it's really a perfect modified blackbody squared. In all those models, you have some distortions, even though they are only a few percent. But the situation is much worse if you fit those spectral parameters not on the EB spectra, but on the EE spectra. That is, you infer what should be the spectral behavior of EB on the EE spectra. And if you do this, the distortions and the differences are huge, like up to a factor of 2 for D12. So the takeaway here is that you cannot infer the spectral behavior of EB from another spectra as EE. It's a very dangerous thing to do because they are distorted differently away from a modified blackbody. And so even worse, if we look at models that are currently commonly used to model the EB frequency dependence, that, for example, we take EE, we multiply it by TB, and we divide it by TE, which is like a classical way to infer what EB should look like. We see that we have strong deviations compared to the actual EB that is in the sky. And the deviations are, are strong for basically every model here. Well, as conclusions, because I will not repeat 25 times the same thing, so I will go quickly on the conclusions. The total polarized intensity is not the local one when you have polarized mixing. Those are the SED distortions. And the polarization angle is rotating with frequency. This is, those two things are consequences of polarized mixing. They have to be accounted for when you want to model the dust signal. If you go at the E and B level, EE, BB, and EB will be different functions of frequency and different MBBs, and also even deviated modified blackbody. They will not resemble perfectly modified blackbodies. The EE over BB quantity will be a frequency-dependent quantity, which provides a model-independent probe of polarized mixing. And finally, as EB is distorted, so it's not the same, well, the closest modified blackbody you can find is not the same as EE, TB, and TE. And also it is distorted away from the modified blackbody in a different way than the other spectra. So you cannot, it's very dangerous to infer EB from the other spectra. They become bad proxies of those complexities. All right, and so just a disclaimer before I conclude. By the time you're watching this video, we must have submitted a paper that is proposing new dust models, which are compatible with data, but which have very high dust complexity coming from the third dimension. And so those models don't have physically motivated EB because they are based on the PySM, but maybe by collaborating with Carlos, for example, we could create some model which have strong motivated dust EB, which also have a weird spectral behavior, a difficult one as the one I discussed here, a tricky one. And so it would be interesting to see if even in those conditions, we are able to make robust tests of cosmic birefringence. So thank you very much for listening. I would be very happy to discuss with you all about this, and I can't wait to see you all at the conference. Bye-bye.